Hello and welcome to our discussion of weather radars. In this video, we're going to talk about the radar equation. So get ready for math. And we'll start out by looking at a radar that really doesn't point in any direction. Kind of like an AM or FM transmission tower that transmits in all directions, or you can think even for that matter a light bulb is radiating visible light in all directions. So the power that's being emitted by such an object we call an isotropic emitter. The power, we're going to call that power P sub T. So that means power is being transmitted and traveling through the atmosphere. Now it's going in all directions, and we can figure out the power density. In other words, how much power there is over a given unit area of a surface sphere, a given distance r from the radar, by the equation, using the equation for the volume of a surface, or the surface area of a sphere, which would be 4 pi r. So this is not the volume of the sphere, but just the surface area of the sphere at some given distance. So if we know what the power transmitted is, we can take that power, divide it by that surface area, and that gives us the power per unit area. And you can see that as the radius, or as the distance is greater from the radar, the power per unit area gets weaker and weaker. Close to the radar, there's much more power per unit area. Farther from the radar, there's much less power per unit area. So that just makes sense, and that's what it shows there, is that the signal gets weaker and weaker as you travel away from the radar because the power per unit area is decreasing. Now, to counteract that problem, what we do is we focus the radar beam. We use a reflector, and that reflector helps increase the power per unit area. Now, how do we describe how much it increases the signal? We use a term called gain, and we're going to use the letter G to indicate the ability to focus the power using a reflector. So if you want to look in terms of light, or want to use an analogy in terms of light, if you had a light bulb that transmitted in all directions, there's no reflector, then you would use the equation on the left, which is the power that gives us the power per surface area traveling away from the light bulb. But since we have, with the radar, we have a reflector, similarly with a flashlight you have a reflector that reflects the bulb, and as a result increases the power per unit area by some factor G. So as the power travels away, as the signal travels away from the radar, it's focused in a particular area, and we call that the radar beam. So the radar beam is the focused power, and it's the amount of power over a given unit area, and that is increased by the gain G. So as the radar beam travels out through the atmosphere, there are targets out there, things that will reflect the radar energy. Let's say that there's a kite way out in the distance. The amount of power that is going to be intercepted by that kite in the radar beam depends upon the area, the surface area of that kite. And we're going to call that A sub sigma. So that's the area of the backscatter. We'll call it the backscatter. And that area, or that power, is simply the power per unit area out at a given distance, of course, times the gain, because that's focused, times the area of that reflector. So that'll tell us how much power is coming back to the radar, or how much power is intercepted by that kite. Now the power that's intercepted by the radar, in other words, what is reflected all the way back to the radar and picked up by the radar, of course, depends upon how much was reflected by the kite. In other words, intercepted, that power that was intercepted by the kite. Then it's reflected back to the radar, so it's got to travel a distance r. And then also it depends upon the characteristics of the radar antenna. So we're going to call the characteristics of the radar antenna A sub E. That is the effective area of the antenna. And then of course the radar beam is traveling back to the radar over a given distance r. As it travels that distance, the power density is getting weaker and weaker based on the inverse of the square of that radius. Very similar to when we talked about the transmitter and the radar actually sending out a pulse towards the target. The same thing happens coming back. As it travels back towards the radar, the signal is getting weaker and weaker because the power density is getting smaller. The amount of power for a given area over that radar beam is getting weaker and weaker. So what we do is we take the power that was received by that target, that P sub sigma, and then multiply it by that factor of the antenna, effective area of the antenna, and then divide that by the surface area, of course, which is 4 pi r, going back to the radar, the distance back to the radar. If you multiply all of that out, you see you got 4 times 4 is 16, you got 2 pi's, you got r raised to the 4th, and you've got the area of the scatterer or the kite and the area of the antenna, and of course the initial power that was transmitted. And then finally G is your gain, the gain of the antenna. In other words, how well focused is that radar beam. That's what we're looking at. Now, the effective area of the antenna is a function of the gain and also the wavelength that the antenna is transmitting. The gain being, once again, the gain that we saw when the power was transmitted. It's very similar when it's returning because it's the same antenna. So we use the same G, or the same gain. So if we put that into the equation, yikes, the equation starts getting a little bit more complicated. You've got the effective area of the antenna is G times lambda squared. Lambda is the wavelength, the frequency that you're transmitting the radar. If it's a National Weather Service radar, that is a 10 centimeter radar. And then the wavelength is 10 centimeters, and divide that by 4 pi, and that's your effective area of the antenna. You can see how this equation keeps getting more complicated and more complicated. So that's the mathematics of how a radar pulse travels through the atmosphere, hits a target, and then the power returns back to the radar. There will be another video that talks about the characteristics of scattering of the target, and then we're going to get into something called radar reflectivity.